In early 2026, inference crossed two-thirds of all global AI compute. The workload that actually runs in production, serving real users and making real decisions, flipped past training in total consumption, and it is not flipping back. This shift means the dominant production workload is no longer the single model API call we see in consumer chatbots. Serious enterprise deployments now look like an agent mesh. Multiple specialized models, routers, researchers, and fact-checkers process shared documents concurrently. These agents share context and hand off intermediate states in real time. To maintain interactive speeds, these handoffs require a latency of under 5 milliseconds. Enterprise AI is no longer a single Oracle problem. It is a highly coordinated distributed systems problem, requiring infrastructure that can handle constant, low-latency inter-agent communication. The standard industry response to these agentic workloads is to throw clusters of NVIDIA H100 GPUs at the problem. Graphics processing units are built for single-stream, large-batch training pipeline parallelism. They are not designed to multiplex dozens of concurrent interactive agents. CortexPod's Cortex chip is a custom inference ASIC designed to resolve this. It is a 12-nanometer chip built specifically for agent mesh concurrency. The core thesis of the Cortex chip is that context switching and memory allocation must be moved out of software and baked directly into the silicon. Software optimization on a GPU cannot fix a hardware mismatch. The physical chip must be redesigned around the communication protocol itself. To see the bottleneck, we can run an 8-agent financial research mesh analyzing a 200-page regulatory filing on an H100 SXM5 cluster. Memory footprint becomes an immediate failure point. Loading 8 70 billion parameter models requires 280 gigabytes for the weights alone, necessitating 4 H100s before any shared key-value cache is even generated. The primary bottleneck appears during interagent coordination within the CUDA Multiprocess Service, or MPS. MPS is the software layer used to manage how multiple processes share a single GPU's resources. When handing off key-value cache on a GPU, the data moves through a mechanical sequence, serialized, routed off the GPU through a PCIe bus to host memory, and deserialized. With software scheduling overhead added, latency per handoff spikes to between 50 and 200 milliseconds. Because GPUs treat interagent coordination as a software-scheduled transfer over an external bus, real-time agent meshes are mathematically impossible on legacy hardware. The Cortex chip differentiator is the Cortex Mesh Fabric Controller, or CMFC. This is a hardware operating system kernel implemented directly on the die. It utilizes a context slot manager to maintain 256 independent agent contexts in dedicated silicon registers. This enables an order-of-one lookup, identifying the correct context instantly without relying on a software page table walk. The CMFC uses a state transfer engine to move delta key-value cache states via direct fabric DMA, bypassing host memory and the CPU entirely. This hardware-enforced preemption reduces handoff latency to under 2 milliseconds at the 99th percentile, ensuring interactive agents are never stalled. By encoding the scheduling kernel into silicon, the CMFC reclaims the wall clock latency that software orchestration traditionally loses. GPU clusters also suffer from redundant computation. When 4 agents analyze the same 200-page document, they each independently compute the exact same key-value cache prefix. This creates 84 gigabytes of redundant cache, burning 4 times the compute and memory bandwidth for identical work. The CMFC introduces a shared read bus. A single 21 gigabyte document prefix is loaded into memory, and a hardware broadcast bus connects this block simultaneously to all 4 agents. This hardware coherency allows direct reads, removing the need for high-latency software caching. This hardware shared key-value cache eliminates 75% of redundant compute automatically, removing the need for an orchestration layer. A common critique of this architecture is the bandwidth gap. The H100 uses high-bandwidth memory, delivering 3.35 terabytes per second, while the Cortex chip uses standard GDDR7 at 1 terabyte per second. This appears fatal at first glance because transformer decode is heavily limited by memory bandwidth, not raw processing speed. The Cortex chip balances this with native W4A8 hardware quantization built into its systolic array. A systolic array is a specialized grid of processors that executes matrix multiplications with very high efficiency. Quantization shrinks the bandwidth requirement. Compressing a 140 gigabyte model down to 35 gigabytes allows it to flow through a 1 terabyte pipe without stalling. Hardware calibration assist registers run online recalibrations during inference, keeping accuracy within 1.4% of the full precision baseline. The hardware compresses the memory demand by 4 times before it hits the bus, making the raw bandwidth difference irrelevant for agent mesh workloads. In the semiconductor supply chain, the industry often falls into the 5-nanometer trap, the assumption that advanced process nodes are mandatory for efficient inference. Shrinking to 5 nanometers adds processing power, but because inference is memory-bound, those transistors sit idle while weights load from the DRAM. DRAM, or Dynamic Random Access Memory, is the high-capacity memory used to store model weights. Cortex chip deliberately utilizes a mature 12-nanometer FinFET process node. FinFET is a transistor architecture that uses a 3D fin to improve efficiency and density. Pairing 12-nanometer logic with standard GDDR7 memory allows CortexPod to sidestep the TSMC CoWoS packaging monopoly, a primary bottleneck in the global AI supply chain. This bypass is a strategic necessity. The 2025 U.S. AI diffusion rule restricts exporting high-end GPUs like the H100 to many Tier 2 Asian countries. Opting for 12-nanometer FinFET secures supply chain independence from export controls and single-point foundry failures. These factors drive the sovereign AI mandate in the APAC market. Data localization laws in Vietnam, India, and Indonesia disqualify hyperscaler API deployments for regulated workloads. Financial and legal enterprises in these regions require localized compute, but they currently cannot access or afford the necessary GPU infrastructure. The unit economics of the Cortex chip address this directly. A single $3,000 chip replaces a $960,000 H100 cluster for a 256-agent mesh, lowering the entry barrier for mid-market enterprises. There is also a drastic power delta. A single Cortex pod operates at 300 watts, compared to the 22,400-watt draw of the equivalent GPU cluster. This hardware allows for the deployment of localized, sovereign infrastructure that remains completely independent of restricted global supply chains. The agent mesh era requires the AI to act as a distributed system, not a single oracle. CortexPod provides the first physical silicon engineered explicitly for that reality.